Thank you and welcome to Heatsink 201, where we will learn even more about heatsink design. Before we discuss new topics with 201, I wanted to go back and review some of the things we talked about in Heatsink 101. In Heatsink 101, we started by just asking ourselves what a heatsink was. We see various heatsinks here. They come in different shapes and sizes, all with pros and cons. My definition of the purpose of a heatsink is to allow for more efficient heat transfer from a heat source to the surrounding fluid environment. And by more efficient, I mean a lower temperature difference. We started looking at the heatsink heat transfer methods. The first one being conduction. Heat can conduct from the die through the lid and interface material up into the base and fins. From there, it's going to convect and radiate away into the environment. We introduced the idea of a thermal budget where we represent it with a 1D thermal resistance, or neglecting any kind of 3D effect, which there are plenty of. But for this is a common approach to help kind of size heat sinks, see how effective an interface material needs to be to meet the temperature requirements. So here we have the junction to case thermal resistance, RJC, the case to sink, which would be the interface material thermal resistance, and the thermal resistance associated with the heatsink, which I call sink to ambient thermal resistance. We also introduced a way to categorize the different heatsink design criteria with first at the device level. Some important factors would be the component power dissipation, the maximum allowed junction temperature, the mounting system or interface material that's going to be used, and the IC package style. Some IC packages are more efficient at conducting heat out the top of the package, some the bottom. There's also some system level design criteria. How much space do you have for the heatsink? The operating environment, what's the surrounding temperature and elevation? Do we have natural or forced convection? And does this have ducted flow, or does it allow for flow bypass? And then there's the kind of non-thermal practical constraints where the heatsink we design has to be manufactured at a reasonable cost, and some heat sinks and mounting methods may be more reliable than others. We also introduced a couple heatsink calculations, one for heat transfer coefficient and the other one for kind of the minimum gap size between fins. And these are good equations for initial sizing or estimating for a given velocity, what kind of heat transfer you're going to get, and for the length of the heatsink, and how many fins should you have. We're going to look at bypass, but as you add more fins, you're going to get more bypass around there. The velocity of the fins will drop. So anyway, we're going to talk about that in more detail today. And we also showed an application example based on the Karma board where we did a modular heatsink design. And today we're going to be looking at the same board, but with a monolithic heatsink design. So we'll compare the results of those. So today's new topics are going to be essentially around heatsink design considerations. First, we're going to look at thermal conductivity. Thermal conductivity, the conduction aspect of the heatsink is very important, and the convection is important, and the radiation, but for the most part, I'm going to focus on conduction and convection, and they're interdependent on each other. So one affects the other. So anyway, thermal conductivity to start. And then we'll look at ducted and bypass flow and look at the difference in terms of what would be the optimal heat sink and some of the specific aspects of the flow. And after that, we're going to talk about heatsink characterization. So kind of what's the methodology used to characterize a heatsink and what can you do with that information? And then I'm going to show an optimization where the primary focus is on varying the heatsink width and length of the heatsink to look at its effect on thermal resistance. And like I said, we have the Karma board application example again, where I'm showing one of the monolithic heatsinks that we'll take a look at. So heatsink thermal conductivity. How important is thermal conductivity? Well, it depends. Like most answers in heat transfer, the answer is it depends. And we're going to not cover everything about thermal conductivity today, but one aspect of it. So we're going to consider an example where we have a component on a PCB in Flowtherm. And then we're going to add a heatsink to that component and vary the thermal conductivity of the heatsink. We're going to vary it from thermally conductive plastic to aluminum. And we're going to look at that in both free convection and forced convection environments. So I set these models up in Flowtherm, and here are the results. So on the vertical axis, I have sink to ambient thermal resistance. Horizontal axis, the thermal conductivity of the heat sink. And over to the right are some dimensions of the heat sink. We can see each line represents a different kind of flow condition. Blue, free convection or natural convection. The way I want 1 meter per second is orange, and then gray is 2 meters per second. But we can see that there's really little drop off on thermal performance when we go from, say, a conductivity of 200, like aluminum, all the way down to, say, 25. So the conductivity doesn't seem to have an effect, or it's the thermal resistance through conduction is kind of being dominated by convection and isn't really a factor until it gets very low. So I looked at these results a different way and just looked at the percent change in thermal resistance rather than the absolute values. So I started at conductivity 200, so that would be 0% change. And as we lower conductivity to the left, we can see what its percent change is. And I've identified where this would be like a conductivity of 3. So I'm saying thermally conductive plastic, I'm going to say it's 3 watts per meter K, 5 and 10. So we can see for forced convection, the low conductivity, you have a 40% change in thermal resistance. Where in free convection, maybe it's 11 or 12% at the lowest conductivity. So free convection, the convective heat transfer and the thermal resistance associated with that is much larger than that of the conductivity. So, for natural convection applications, there really isn't a huge benefit in using, say, aluminum over a material that has a much lower conductivity. Not thermally speaking, but until prices come down on other materials, then aluminum is the choice that is made. But it's not purely based on a thermal reason for these cases. Now, later on in future webinars, we'll continue to talk about conductivity. So this is just one aspect of thermal conductivity. Next thing I'd like to talk about is ducted versus bypass flow. So what is bypass and how does it affect the optimal design? So we have ducted. With ducting, the air is forced between the fins, so more fins result in a higher flow impedance across the heatsink. With bypass, adding fins forces more air to go around the heatsink, so less flow passes through the fins. So that's what we're talking about, ducted versus bypass. As the number of fins increase, the air velocity within the fins decrease when we have bypass flow. And we see for the case on the left with 8 fins, we essentially have the same velocity within the fin gaps as we do as the approach velocity. Adding 12, the velocity goes down. We could start to see it really blocking the flow downstream. By the time we get up to 15 fins, it's really blocking the flow quite a bit. Now, we don't necessarily, just the higher velocity doesn't mean that's the best heat sink. We'll see later that this is actually the best heat sink. So it's a balance between the airspeed in the fins and the surface area. And that's really why CFD is great. You can analyze that sort of stuff. If you don't have CFD, a good way or an initial way to estimate it is there's a good article on the Electronics Cooling magazine by Robert Simmons, estimating the effect of flow bypass on parallel plate fin heatsink performance. And if you look at this site, you'll get equations on how to estimate the velocity. So that combined with the equations that we previously introduced, you could estimate the heatsink thermal resistance. He's done that. He's plotting it here. You see this lower line is without flow bypass. So we see it has an optimum, but a higher number of fins than the condition with bypass. And as you go away from the optimum, the curve is less steep than it is when you have bypass. So that's kind of interesting. I ran the same type of situation in Flowtherm, where I have basically the heat sinks we saw a couple slides ago, where I look at the thermal resistance when it's ducted, this blue line, and then with bypass, this orange line, both at 2 meters per second. So I'm seeing the same type of effect as the previous table showed, the previous chart, where with bypass, there's more pronounced optimum. With ducted, the optimum is a higher fin count, lower thermal resistance. Yeah, certainly the velocity is going to be higher in the fins, and departure from that optimum is much less steep. So you got to look at pressure drop when you're talking about ducted flow. So we could see the pressure for these different fin counts increases linearly with increased number of fins. For the bypass case, really there's no effect on the pressure drop, as the air just, rather than increasing the pressure, the air just moves around the heatsink. So there's a price to pay. So really when you look at a ducted system, you don't have the opportunity to fix the velocity. You have something driving that flow like a fan that has some kind of characteristic curve. So let's take a look at that. So I analyze the model in Flowtherm with, rather than fixing the upstream velocity, I use it with a fan. So that's the gray curve right here. You see in each chart, I am identifying the optimum with these large circles with the border. We can still see what the optimum is. Anyway, yeah, so we can see that in this case, the bypass versus the fan produced essentially the same thermal resistance as an optimum. Just a coincidence. That's a coincidence. And the optimum number of fins, depending on the fan that you have, could be higher or could be lower than these other values. Because we're talking about ducted flow, I thought it'd be a good time to talk about heatsink characterization, because that's typically based on a ducted flow environment. So a heatsink characterization provides thermal resistance and pressure drop versus approach velocity for the heatsink. And this is something that vendors would provide for heatsinks that are used in a forced convection environment. Vendors will typically fit the wind tunnel cross-section to the heatsink with very little bypass. So they limit the room for the air to go above the heatsink or around the sides of the heatsink. And they would also typically mount the heatsink so the base is flush with the wind tunnel floor. So the flow is as uniform as possible coming across this heatsink. And lastly, they're going to apply the heat uniformly, because any kind of heat spreading through the base is going to give higher effective thermal resistance to that heatsink. I was asked after Heatsink 101, is there any standard? And I'm not aware of any standard for heatsink characterization, but vendors generally report data based on the same measurement environment. So they're all very similar that way, I believe. Metrics are provided for comparative purposes and are not typically used directly in a design. So the way this test environment is going to be different than your system environment. It could help you compare heatsinks from different vendors, look at the pressure drop versus an applied flow rate and the resultant thermal resistance before you go to the next step. Just to take a look at that, the airflow in the characterization environment is different than the system. So the airflow in the measurement environment, is going to be nice and uniform. But when we go to system flow, and this is that heatsink in bypass, we could see that the air can leave the top of the heatsink, and also we've got a whole bunch of recirculation going down at the back end. Quite different. So this environment's going to give you a different performance than the measurement environment. So be careful. It's great data for the vendors to provide it, but you can't just design only with that data, is the point I'm trying to make. So if you did have a ducted system and you had a fan, how would you estimate the performance of that system? So we have our thermal heatsink characterization information, the thermal resistance versus approach velocity, and the pressure drop of that heatsink versus approach velocity. And I've also plotted the fan curve. So this would all be, say vendor provided data. So we identify the intersection of this pressure drop curve and the fan curve. Then we go vertically upwards till we intersect that thermal resistance curve, and then over, and then we can estimate the thermal resistance of the heatsink in that system. Again, it would just be an estimate to get you in the ballpark of where you need to be. Okay, the next thing I'd like to discuss is heatsink width versus length optimization, and what is more important. You probably already know the answer to this, but it's interesting to look at, I think. So there's a heatsink. What is more important, the heatsink width or the heatsink length? I used Flowtherm to study this. I set up a design of experiments. In this image here, we're seeing what the base case heatsink looked like. So what I'm varying in this design of experiments is heatsink length, so 33 millimeters to 99, so I'm showing 33, so it's allowed to go 3x. The heatsink will always stay centered on the component. And I'm varying the number of fins, so rather than varying the fin width directly, I'm varying the number of fins, and then I set up a linear constraint in command center so that I can maintain the constant fin gap. I felt like this would give me a better one-to-one comparison of length versus width. But I just want to point out that this really isn't a width optimization. It's more of a study, but I'm using design of experiments, and then I do some optimization also. But anyway, I just want to make that point. I also included base thickness, so I allow the base thickness to go for anywhere between 3 and 5 millimeters. So the fin height changes with the base thickness to maintain the same heatsink height. So I think that's probably a natural way to do any kind of optimization in many cases, because you have a specific volume, and lots of times it's a balance between fin area and base thickness, especially as the heat sinks become oversized and there's a spreading resistance through the base. We talked a little bit about heat spreading in Heatsink 101, but that'll be a focus on the next webinar. For now, we're going to look at this. Constant height heatsink. 30 designs were simulated, and all I'm trying to show you here is the distribution of the design of experiments. So we try and get equal coverage for each variable in that design space. Lots of runs here. And then the output I have is junction temperature and heatsink mass. Again, the thing I want to illustrate here is that I was easily able to create a lot of models and solve them. It was easy to generate a lot of results. But the difficult part is trying to interpret these results and know what is better and what is worse. That's where the optimization comes in. So I used response surface optimization, which takes the results of the design of experiments, and it does two things. First, mathematically, it tries to estimate where the optimum is. So what's the optimum width and length and base thickness. But it also gives you the plots and data to study the sensitivity of these design inputs, which I think are just as valuable really as the actual optimum. So anyway, with that one set of design of experiment results, I did two optimizations. The first one was to minimize the heatsink mass whilst attempting to maintain junction temperature below 95 degrees C. The second optimization was to minimize the junction temperature. So here's the results of optimization 1. So to minimize the mass, the optimization decided that it didn't need to grow the length. So the heatsink length is the minimum value in my design space. The maximum number of fins I could have is 36. So this heatsink isn't the full width that's possible. But it did grow the width until it satisfied this 95 degree C target. And then also chose the thinnest base thickness, again, because it was trying to minimize the mass. One point I'll make here is that the cost function was to minimize the mass. There was an output constraint to hit this 95C. So when I ran the CFD results, so I took the output of the estimated optimum, ran it with CFD, this was the actual junction temperature. But I just wanted to point out that this junction temperature wasn't the cost function, so slight difference there. For the second optimization, I wanted to minimize the junction temperature. So in this case, it went to full width allowed with 36 fins. It went to full base thickness, and then grew the heatsink length to 82.5 millimeters, where 99 millimeters was the maximum it could have gone to. So going beyond 82.5 wasn't going to benefit the heatsink performance because of the air being allowed to bypass, so it cut it off 82.5. The minimum temperature was 76.5 degrees, about 20 degrees less than the one where we're trying to minimize minimize the mass. But then I thought, what if these heatsinks are made out of copper? What kind of performance would we get then? If the heatsinks were copper instead of aluminum, for optimization 1, the temperature drops about 7 degrees, and only about 4.5 degrees in optimization 2. I was kind of surprised a little bit. I thought that I might get better performance increase with the higher conductivity material. In this case, it doesn't really warrant the, over 3x increase in heatsink mass, probably. That was kind of the one output from the response surface optimization. What are the optimums? The other aspect is trying to study the effect of the input parameters. So I took the data from the response surface optimization and created these two plots. So on the horizontal axis here, we have the increase in heatsink dimension. So the x, 1.5 times the initial length or width, 2 times, 2.5 times, and so on. This orange line is the heatsink length. So you see, certainly before I get to 2x, the benefit of increasing the length is there's no additional benefit. And the total benefit, doesn't increase beyond 10%. Width, I have much larger benefit in going with width, but it's not linear. I believe that if this heatsink were a perfect conductor, that this heatsink width would probably be a linear variation. Let me know if you disagree or have other ideas, and we can explore them and write about it. Anyway, so I think, this effect in large part is due to the heat spreading through the base, and how as these fins get further and further away from the heat source, because of the inefficiencies in conduction, I don't get the same benefit as if they're closer. So interesting, I think. As we probably knew beforehand, width more important than length, but this just kind of illustrates it. So onto the application example. So this is the Karma board thermal design used in the Owen Valley Radio Observatory at the California Institute of Technology. Just to review some of the particulars of this example, we have the flow direction is from bottom to top. All the components are dissipating 13 watts, not very high power really. So it shouldn't require any too aggressive of a heatsink solution. TJ max 95 degrees in an ambient of 35. Again, kind of relaxed constraints there. It did have one interesting constraint where to try and maintain these component temperatures within 5 degrees C of each other. And that is to do with the operation of the board, the timing of these ICs. And we see the interface material is 1 degree C inch squared per watt. In the previous example, I used the same interface material because it's low power. It doesn't really require anything too exotic for interface. But with monolithic heat sinks, typically, you're going to be required to have a interface material that can compensate for the tolerance in the component heights and make sure that this heat sink seats properly on all the components. So I think a interface material resistance of 1 is probably a reasonable assumption. To just review the results out of the Heatsink 101 design optimization, this is the heatsink dimensions, fin heights for this modular heatsink design, and the design setting optimization was almost all those components are exactly the same temperature. So it worked well, but many people pointed out during the webinar and after that monolithic heatsinks are a great choice when trying to maintain components at the same temperature. And I agree, connecting components through conduction is a great way to make the hotter component cooler and the cooler component hotter, bringing them together, and then convect the heat away at the same time. So anyway, it's a good choice. We considered 3 designs. The first one I'm calling radial, and this is based on a sketch on a napkin, and I'll explain the theory why someone thought this might be a good idea, and it turned out it wasn't a bad idea, actually. Probably not good enough to warrant the additional costs required probably to make that heatsink. The second thing we looked at is just the plate fin heatsink, and third, we looked at that same heatsink but with some crosscuts that are strategically located. They're not uniform. Let's just say they're not uniform. They're placed there for other reasons besides uniformity. Anyway, we want to look at this because coming out of Heatsink 101, people were asking, rightfully, that as flow moves down a channel, get to fully developed flow, and if we can have a crosscut to both maybe introduce some cooler air And also to reform the boundary layer, would we get more efficient heat transfer? We did a Q&A paper for Heatsink 101 afterwards where we kind of explored this idea where the sacrifice in surface area for convection, you don't get something for nothing. So losing a little bit of surface area wasn't compensated for by any additional crosscuts. And that's, what we said was generally true. When we're looking at these things, I want to see like what I would say is sledgehammer. So if I see say a 1 degree difference in a 30-degree temperature rise, I'm not sure I'm going to spend a lot of time optimizing around that parameter. Anyway, that's my opinion. So anyway, these are 3 heat sinks we looked at. And let's just look at the temperatures. So I have one legend for the plate and crosscut, and then another legend for the radial. It was operating at a higher temperature. Primarily, I believe, because it's got a lot less surface area we can see here. So a couple things to note. We could see slight differences in the surface temperature of this heatsink, but not greatly. Not maybe enough to warrant an extra step in the manufacturing process of this heatsink. And this probably did not perform well enough to warrant any additional costs in manufacturing. But the idea behind this design was, one nice thing is it's kind of organically got less surface area upstream than downstream. So, it kind of balances how the heat's going to be rejected because you have more surface area to reject the heat down here. The other idea was that once the air enters the channel, it will accelerate down the channel, providing better convective heat transfer as you move down the channel. The third reason why this was a novel idea, in theory, was that these channels were set up in such a way that cooler air could be introduced on the sides. Now, these fins, are not optimized. Probably have more fins, less fins, different angles, and look at the effect. What we wanted to begin with is see, did this initial sketch on a napkin warrant any further investigation? Our decision was that it really didn't, but it doesn't mean it was a bad design. It's just that it's probably going to be hard to improve over this base performance. As far as junction temperatures, the radial is higher than the plate and crosscut, but it's the one that matched the 5-degree delta T more closely. For this example, in this design, it would probably satisfy the constraints of the design. Where these don't, they're well below the maximum operating limit, but there's about a 10-degree delta between the forward and rear components. But I think that could be easily compensated for by having a thicker base. So again, let's use that connection through the conduction process between these components and improve it by giving it more cross-sectional area to conduct heat through. So I think that could be taken care of. And also, if we compare the junction temperatures between the plate and crosscut, we'll see there really is no significant difference. So some concluding remarks. Heat sinks are not as simple as they look. There many times, and most of the things I've looked at are kind of simple extrusions, which seem simple, and convection, conduction, radiation certainly aren't complicated topics really, but they aren't as simple as some correlations and a surface area. The correlations shown are useful for some initial sizing and studying of the trends between some design choices, like ducted versus bypass, more fins versus less fins, heatsink length versus heatsink width. But you certainly wouldn't want to base your final design on correlations, I don't believe. Not today. And performance metrics are best used for comparative purposes. So while the vendor provided data is valuable, it's difficult to be able to take that, like any performance metric data, component level, heatsink level, fan level, it's difficult to know exactly how that's going to perform once you place that in your system. Heat sinks, I believe, are especially true. Heat sinks are best designed for a specific system. And I'm going back to what we were just talking about. You can look at the characterization data, but really not have a great idea how it's going to perform in your system. We see a strong interaction between the heatsink and the surrounding flow. It's going to affect its performance. And we looked at an example where conduction and convection are interdependent. So it's best studied all at the same time in the system environment. My recommendation, design the heatsink in situ, ideally with CFD. Do some initial sizing, like, hey, can we cool this component with this much space? Correlations would be great for that, I think. Yeah, it looks like we could do that. In terms of designing that, I would use CFD. And in terms of validating the design, certainly you want to use measurement.